And these Gaussian functions is incredibly interesting. So I'm going to write over here, but I'm not going to erase. Oh, I can erase some of this. And so some of these Gaussians, which we call hyperGaussian functions. And this turns out very, very useful. This turns out very, very useful. So the hyperGaussian, the regular Gaussian is x squared. HyperGaussian can be x to the 8th, like this. And you put the coefficient, whatever, let's call it a squared, like this. These are called hyperGaussian. HyperGaussian is very useful for the Fourier transform. I wish I knew this when I was undergraduate, but unfortunately I had to learn the hard way when I was doing the research. It's kind of a real tough things to learn. But later on we learned it. Okay. Two mechanical bosons have zero energy at 0K. No. So you always have non-zero energy. Good job. And the main reason is, what's the main reason? Why this boson cannot have zero energy equals zero? Fundamental reason. Exactly. Good job. Yes, uncertainty principle. Okay, so that's end of my PPT, and I'm going to stop sharing, and I'm going to end the Zoom. All right. Any questions before I move on? And make sure you guys do turn in the homework, so that way I will grade them and on time. Okay, so that's it. I think I'm pretty satisfied with you guys doing. And this is the question link. I will assign you homework for you guys, and after I grade them today, I am going to move on to the last point of this section. And this last point of this section, I am going to keep some of the relation here. I will keep this relation, but I will start with the bottom part to save my space here. So this will be, I think it's called item number 4. This is number 3. Now we're going to move on number 4 here. So this is called Eigenstates and Probability density. So probability density. So that's what we're going to talk about today. Last time we just showed you how to get ground state, but we did not show you how to get systematically all the rest of these eigenstate, and we also did not discuss the probability density. So these two features will be illustrated here today. So I'm going to keep this permutation relation here because we will utilize them very, very intensively. And I move this Hamiltonian over here to obtain other states, other eigenstate. But other eigenstate, we only got a ground state, but that's not most exciting. We want to get other the rest of the states, which we want to get. And I'm going to show you how to get these other states. Suppose I have suppose I already got an eigenstate. So this is the Hamiltonian, and this is the eigenstate itself. Now these are all assumed. I didn't say they know yet, but we're just assuming this way, like this. And so because this Hamiltonian, you remember we have operator like this, so we're going to plug this operator directly over here. And A dagger A. I'm copying this part over here. I didn't do anything else. H omega phi A to the N. phi n. So this is what I have before. Now, when a dagger A applied onto this phi sub n, so I'm going to write this down. A dagger A apply this n, so this particular part, remember without the 1/2, this part applied onto this, and this is going to equals n. N is a quantum number, start from 0 all the way up like this. And this is assumed. So now everything that I wrote over here all assumed. I didn't prove it, I just assumed this way. So then you can see when I plug this guy plus on top, I will get n plus 1/2 h bar omega phi n equals En. Again, everything that I wrote down here is all assumed. I did not prove it. And I will prove now. So now you can see the eigenenergy for the harmonic oscillator En will be n plus 1/2 h bar omega. So this is my assumption. So I always have eigenstate. I always arrive this way. From here to there, it's not assumed. This is assumed, but this is not assumed. This is because of the harmonic operator we proved last time can be written this way. So the remaining steps, including this particular step, we will show you why this must be n as well. So that's what we have here. Are we good so far? So that's what we have. Now, what we want to prove is that any eigenstates can be found with the a dagger operator. All the other states can be found by the dagger operator, which means, let's say I call phi prime. Any phi prime, it will be also an eigenstate. So we are going to prove a dagger n phi sub n is also eigenstate. So this is going to prove. We're going to prove this now. Is also an eigenstate. This is also an eigenstate. We haven't done it yet, but we will prove this will be also an eigenstate. So we are on the way to prove this now. So this is our idea, which we will try to get this across. Let me tune this one. Okay, very good. So this is a relation which we prove. Okay. Now the proof slightly complicated. I'll just warn you for the moment. So in order to prove equation number 1, which means we need to prove phi of the Hamiltonian applied onto prime equals E prime phi prime. In other words, when I say phi prime equals a dagger phi sub n is also an eigenstate, which means equivalent, I'm going to prove this particular relation. So they are. If I can prove this, then phi prime is really an eigenstate. So this is a job which I'm going to do it now. So that's what we have. I want to show you a step-by-step fashion so you can see how this works. It's non-trivial. So that's why I want to purposely show you this one here. All right, let me get started. So I'm going to do a step-by-step fashion. Step number 1. So step number 1, we're going to start with the h hat and phi prime like this. So we're going to use h hat phi prime. Phi prime is this particular term, so I'm going to replace that. A dagger hat and then phi n. So this is my. I started using that equation directly. Use that. Any questions so far? I didn't do anything except I just plugged this guy into here. So that's I want to prove. And so that's a relationship. Now, whenever you see this, our focus is on this particular term. We will currently we will ignore this one. We just look at the operator side. So let's look at the operator. You notice that the operator h hat just equals, I'm going to work on this, h hat, a hat, dagger. This is going to equals a dagger, a hat plus 1/2 h omega. So that's my h hat. So that is what I got. And you notice that I also have the a dagger at end. So this will be a dagger at end. So this a dagger is that a dagger. Okay. So I have two terms now. Let me expand this term, two terms. So my first term will be this part times that. So will be, I'm going to move h bar omega to the front. So make things a little easier because these are just classical numbers. I can swap them, exchange them without any difficulties. So this is my first term. Second term is the 1/2 h bar omega a. So I have this particular part. Now the second strategy is always like there's no exception whatsoever. The step number 2, these triple operators, we will convert these triple operators, move a dagger, our job is a dagger hat, move to the end. I'll explain what this means. And so the second step, we're going to, within these triple operators, we're going to move a dagger a to the end. And I'm going to show you in the next part. So I'm going to show you over here. So that's what I'm going to do. So this is the most critical point. In other words, we always move a dagger a to the end. So we always move this a dagger a to the end. So this is our job. Okay, so let me summarize what we did. Well, first step what we did, we just plug in the Hamiltonian operator and get this expression. We have two terms involved. The second term is settled. There's nothing you can do with it. The first term is not in good shape. So our job is we're going to move a dagger a to the very end. That's always the case. Question, why? So why we want to move a dagger a to the very end? So what is the reason why we want to move that to the very end? Why do we do that? Well, because if a dagger a is at the end, then a dagger a is going to directly apply to this function. Because that guy will be at the end, so it's going to directly apply to this function. Now watch carefully. This part is just equals n phi sub n. And that n is the quantum number. Did you see the trick here? In other words, this particular relation, once I move this term to the very end, I can simplify a dagger operator to directly become a quantum number times the wave function. So you see, when a dagger a apply the phi sub n, it becomes n times phi sub n. That's our job. Does it make sense to all of you? You know, our job is we want to move this guy to the very end, and then you can apply the wave function. When you apply the wave function, you get a number. So then you can simplify things completely. In the homework, we do similar like this. If we have a, not a dagger, we do the same thing. Essentially, everything what we do, we just move this into the very end. So now, how do we move this a dagger a to the very end? So now we understand we need to do this. Now let's do that. So with a dagger. So this is a term which we have. So in order to do this, well, we do the following. So in other words, this guy has to be moved one step further, when they're over here, like the mode. So these two has to be swapped. So what we do the following. We're going to use this permutation relation. Folks, take a look at this. So this is the permutation relation which we're going to have. And you see that the A dagger minus A dagger A, this is going to equal to 1. So this is going to equals 1. Oh, forgive me. I forgot this A dagger, folks. I missed it like this. So here's A dagger, not A. So that's what we have here. So in that case, what I need to do, what I want, I move this term to the very beginning, and these two to the back. So that's our job, which we're going to do right now. So essentially, we're going to swap these twos. Oh, that's our job. So then you can see A dagger A hat is going to equal to 1 plus A dagger A. So this means this term is going to equal this term there. You good? It good so far? Anybody have questions? Alex, you good? So essentially what we're doing, we treat these terms here. So essentially what we do like this. Swap them. So then you will see A dagger 1 A dagger A. Like this. So A dagger A, that's what we'll get. Now we succeeded. Why? Because this guy is to the very end. The very end. So now we're going to plug the phi here. So step number 3. Multiply by phi sub A. So this will be equation. Let's call it equation number 2. So equation number 2. So in the equation number 2, we're going to multiply by phi. So this will be eventually get us the results. So we're going to multiply by this term by phi. So let's do that. So A hat 1 plus A dagger A phi A. So that's what we get. Now when these operator apply to this, the first term is 1. The second term is going to be N, phi N. So that's N. Are we good? You know what we're using? We're using this relation here. So A dagger A phi N equals N times phi N, like that. So then we can combine all these two terms together. 1 plus N is a classical number. I can move to the front, make things look nicer. A dagger phi N. Are you guys with me so far? So far so good, so far so good. Everything's good. You know what? That is what we do here. So now we almost are there. So we're almost there. And let me call this term. Folks, could you add, this is term number 1. This is term number 2. So that's term number 1, term number 2. So our term number 1 is going to be h bar omega multiplied by this term. So term number 1 is going to be h bar omega multiplied by 1 plus N A dagger phi N. Our term number 2, this term number 2, h bar omega 1/2 A dagger phi N. So that's first term, second term, and multiply by each other. And now you notice something very, very interesting. And this is what I have on the left-hand side I will get. So I'm going to add these up. So I'm going to move the camera over here. So all I need to do now, things becomes much simpler. I add these two terms up. So once I add these two terms up, and that's the final results. And this is our final results. So the final result, step 4. Final results. Our final results is just 1 plus 2. It's going to equal and will be h bar omega n plus 1, n plus 1 mode n to the front, same thing, plus 1/2 over here. And this part is going to multiply by a dagger, and like that. So that's the 1 plus 2. Now, this part is just phi prime. Did you see here? That term is just phi prime. So then you can see my left-hand side is h hat phi prime. So this is my left-hand side. Is going to equal the right-hand side. You can written e prime phi prime. So that's h phi prime equals e prime. So you see, I proved it really the eigenstate, because this equation it just show you, except the eigenvalue is going to be changed. Did you see added by 1? Did you see added by 1? But in the beginning, we do not add by 1, just like this. N plus, you see, n plus 1/2. There is no add by 1. But newer energy added by 1. So that's why the ladder operator, what it does is actually increase the energy by 1. That's why it increased that. Makes sense? And this proves that way. So the incidence part is this particular portion. So this step is the most important. Step number 2 is the most important. You always remember you have to move a hat a to the very end. A hat a to the very end. So that's why that is you can apply that to this. Now when you got this, so and then you notice that all these calculations, if I got phi 0 in the ground state, and a dagger will be the excited state. And all subsequent ones will work, because I did not choose a special one. I just choose the arbitrary ones. That's why I keep on going. And this will lead to phi 1. The expression I will show you quickly. And I want to give you a notation simplification. When we write a phi, it kind of takes time. But when it's a direct notation, in the future, we will denote in the following way, like this. We use just an n to represent that. Alex, this will be the same thing in direct notation, but we use a quantity number instead of phi sub n, but mean the same thing. So this is the simplified notation to make our illustration quicker. And I would like to show you the probability density. This it will probability density. And this part is really interesting because, well, end of the day, we want to compare with experiments and what we have. So I am going to show you. First, let's go to figure 3.2. And I forgot page number. Let me get page number. 3.2. I show this. I don't know whether the electronic version, where that is. Oh, let's do 3.1. Forgive me first. Yeah, forgive me. Let's go to 3.1 first. Forgive me. Well, let's get. And this is on page 65. I don't know whether the electronic version is which page that I don't know. Okay. Yeah, take your time. On page 65, on 3.1. Which page? Electronic version. 43. 43. Okay. 43. Is that always differs by 22 pages?
Yeah,
sometimes yes. Oh, okay. All right. Everybody's on 3.1 figure. Okay, very good. So on the left, you see we draw on the potential. That's the harmonic potential. The one is a real potential. That's the Landau-Jones potential. Is solid line. That's A. And the particle is oscillating in the harmonic potential. That's oscillation in the, you have equilibrium in that location. The right-hand side is a classical probability density, and you can read from page 64 all the way to 65. And I read, when I got the figures like this, and I really like these books have these figures. But unfortunately, very few books actually have this equation, so we decided to derive this, and that's the equation which we have. And you notice that classically, the harmonic oscillator has a probability density look like this. And it's got the straight lines come down like this. Now, these two straight lines, when we plot them, did you see this straight line is not really straight? It turns out when x is 0 to minus x, because we use the probability density, you see, classically rho sub x equals pi square root x squared 0 minus x like this. So you see, when x equals x0, which is here, this goes to infinity. So that's why in the figure, when we plot them, we just cut off some portion. Otherwise, this is going to go to the infinity. So that's what we plotted. And so this tells you that essentially the probability density at this particular end is going to infinite. And of course, this makes sense because the probability density is infinite. Doesn't mean the probability is infinite. So that's the difference. Okay. Because it's just one single point is infinite doesn't mean the whole thing's going to be blow out. No, it doesn't. So that's the probability density. And now, in order to determine, you remember, in order to determine this x0, you have a spring, like, yeah, here's a spring. And this is actually non-trivial. You look at my spring, can you see my spring here? Can you see my spring? If you look at your spring, you see how much you stretch that matters, right? If I stretch very little, it's also like this. If I stretch a little more. And this is what we call x0. x0, which means how much is deviation from that point. So how much deviation? When we start to plot this and we're running the problem, how much we stretch them, and a lot of books just sketch schematic to show you this. It turns out they were wrong. What we need to do, we need to use the following equation. I'm going to write this down. This is in the caption of our figure. We must use this relation. This is a classical energy, potential energy. Folks, this is classical mechanics. This is the classical mechanical energy. And this has to equals quantum mechanical energy. This has to equal quantum mechanical energy. This should be, there's no zero here. And these two has to equal to each other. In other words, you cannot say, I'm picking up x0. Well, how large x0 you got? And this you have to do like this. So this is the quantum. And I saw a few years back, there is an APS meeting. Somebody plot some equation on their shirt. And this is the one that showed the equations. Classical word, quantum word. It was just amazing. So in other words, you see the quantum word, you have to tell me how large n that is. How large the n that is. And you have to tell me how large the n that is. So when you determine how large n that is, then you can determine how large x0 is going to be. This is truly non-trivial. When I plot this and I say, oh, how do I know x0 that is? This is how do you get that. So that's why when you write a book versus just simple teaching from a textbook, you hopefully student never ask you questions at all. But when you write a book, you still start to scratch your head. How do I get x0? I know there's x0. Usually you say, well, look at this classical operator, but actually that's how you do it. These are extremely detailed. You also notice that the caption on the x-axis, you see I used the eta. We did not use the, did you see we used the alpha times, did you see alpha times, sorry, this is the alpha times x. And if you directly use, and this alpha times x is also very, that I, it's actually a. Okay, that's a. Anyway, it just looks like an a, x. And this you have to multiply onto this. It's not just a regular classical, otherwise you get it wrong too. It took me about a month to figure this part out. Now you see in the book in a few minutes. That's non-trivial because when you plot them, your horizontal axis must have no dimension. This you only have no dimension. Otherwise, you have dimension. You plot things wrongly. So that is the trouble we have. And this is the classical probability density, which we love that. So that's where you get it. Any question on this? Okay. Now can we go to figure 3.2? Let's go to figure 3.2. This is on page 68. And are you there? So there, see that? 3.2. Everybody there on there? Can I get a thumb up if everybody's on that page? Okay, very good. So you see, the left-hand side just show you how these the ladder operator tells you. Now this A dagger, we also call. Could you guys write this down? This is also called creation operator. Could you guys write this down? This is a ladder operator, but this is also called a creation operator. It creates something more. And then the A itself, this is called an annihilation operator. You annihilate some of the particles. That's called annihilation operator. So these two have different names. We annihilate some of the particles. So that is why we call it annihilation of the operators. So this is the one which we want to show you. And now, once we understand this, we can take a look at the wave functions. You see the first wave function, 3.2b, the first wave function is a Gaussian, but second wave function starts to have a little oscillation involved. Did you see you have a node there? And this, whenever you have more nodes, this means higher energy. Could you guys write this down? Higher energy. So this means have higher energy. You have more nodes and always higher energy. One last figure is 3.3. 3.3, did you see we have a wave function 5 sub 10? It took me a long time to figure out this. How do we get 5 sub 10? Crazy, you got the 2 1s, easy. And in the homework, you're going to plot the same wave function that I did. We use the Hermitian Hermit polynomial. In our math physics 2, we talk about Hermit polynomial. Hermit polynomial, it has a recursion relationship. So I'm going to write this down. It has a recursion relationship, look like this. Eta to eta h n minus 1. So these are all Hermit polynomial themselves. And minus 2n minus 1 and times h sub n. And the main reason I want to write this down was that when I try to use equation 3.2.17, it's so many derivatives make my brain a lot. If you take derivative 10 times, Cody, your expression looks like this long, right? 10 terms. I go to the internet, they didn't have 10 terms. My gosh, that's 2 lines, all this. When you write a program, I can't do it like this. And this one is also for recursion relation, it's actually much simpler. So in a program, actually that's what we did was we used the previous 2 lower order, give me high order, and then iteratively solve for this. So that's how do we get these all wave functions. And then 3.3, you now see part B. You see we calculate probability density. You see the classical ones and the quantum ones have a little bit of leakage on this side. It's similar like this, and then it comes out like this. So classical one stops here, classical one stops here. The quantum mechanical ones will be a little bit squeezed out. So this part will squeeze out. That's the way the quantum mechanics results. And again, you're going to use our program to plot these ones, and I think you will like it. And this is one of the things that I always found quite interesting. Oh, I ran out of time quite a bit. Any question before I move on to the next? So we showed you how do we get these eigenvalues and how do we get these eigen functions and called probability density, and that's almost the end of it. So now, one last part of this particular, the ladder operator is how do we use them? So this will be new section. How do we use them? This new section relatively straightforward, and I'm going to show you section 3. Let me show you section 3. This application of ladder operators. The ladder operator, when you do some research and you found a ladder operator are very, very useful and sometimes extremely helpful for you to get these results quickly. So this will be section 3. And I always want to have some applications. Some books always skip this part very, very quickly. And I think this part as well, you actually can learn enormously. So we're going to use those ones to compute some observables, and which I'm going to do right now. So first, why we use this in the first place? Let's look at the traditional way. When we use the traditional method, and then when you do that, you will find something quite non-trivial. For instance, if I want to calculate expectation value of the position, you have to first find the wave function itself. You look at the Hermitian polynomial, we have that. It's quite complicated if you have higher order ones. Similarly, for the momentum operator, you have similar difficulties. So it's essentially very, very challenging. But when you have the, if we use a ladder operator, and things becomes much simpler. So essentially what we have, we do the following. So we know h hat equals 1 over 2m h bar omega, and then we have m omega x hat plus I p x hat, like this. And that's a hat operator. A dagger just the Hermitian of the previous operator, that's Hermitian. Again, this part doesn't change at all, and you only change this sign here because the x and omega, px always Hermitian, so this will be named ipx, like this. And now you can see I can calculate x hat and p hat using the a dagger a. So what you will see, I'm not going to write entire things out, because you can clearly see, you can write in the following format. So x is going to equal the sum coefficient in the front, a dagger a, like this. So you always can do like this. Add these up, so these two terms cancel out, and some coefficient in the front. Similarly, p x hat some coefficients and minus each other, like this. So now you notice that when a dagger a appears some in the simultaneous, the same equation, it's a physical. If a single one does not mean anything, but this is a physical now. So then you can see, if I want to calculate expectation value of x, all I need to do expectation value of this, expectation value of this, expectation value of this. So that's all I need to do if I want to calculate. If I want x squared, like this, some coefficients will be a. I want to calculate like that. And then you're going to see a dagger and a dagger like this. So if x squared. Similarly, you will get a p hat x squared, some coefficients, a minus a dagger, a minus a dagger, like this. Did you see you can calculate the x squared of p squared simultaneously if you want to use it? And the question is that what is the matrix elements for P, X, and X? So this is my job over here. Found A, N. So we want to find how large this one is going to be. So I'm going to borrow about maybe 2 minutes, 3 minutes. Is that okay? Just borrow a few minutes because I can conclude this now. Suppose I want to find a hat applied to N. I wonder how large this guy is. All right, so this is my job, which I'm going to show you now. So a hat N, and we want to how large this one is. As I said before, this is always lower the quantum number by 1. That's always. So in other words, this state has to be equal to N minus 1. So there's no question about it. And this has to have some function. Function on the top. Could it make sense to you? So with A applied to N, it'll be N minus 1 because you lower the energy level, so that's why it's N minus 1. Make sense? Make sense? Now, next step, we're going to do the Hermitian conjugation. So that's Hermitian conjugation. Hermitian conjugation, which means I put this all to the star and flip them over. So this is what I will get. And hat, a dagger. And this will be left-hand side. I make A as a real number, so there is no change whatsoever. So that's what I have. So I have 2 equations, 1 and 2. What I'm going to do, I'm going to do 2 multiplied by A. Oh, so 1 multiplied, sorry, 2 multiplied by 1. So this is the next equation, which I'm going to show you now. 2 multiplied by 1. So that is what I'm going to do. So then you can see this term on the top will be N. Sorry, this will be N here. And then a dagger hat, A hat, N equals N minus 1 A squared N minus 1. So this is equation number 2 multiplied by equation number 1. So that's on the left-hand side. Right-hand side, equation number 2 multiplied by equation number 1. So now this is left-hand side, this is right-hand side. Now this will equals N squared. Because N minus 1, N minus 1 is normalized equals 1, 2. And this term here, this just equals N. And like this. And so therefore, here I use the relationship. Could you guys write this down? Everybody write this down. I insert a relationship N equals that. And I also insert a relationship A dagger A N equals N like that. This N is just the classical number. I move them out. So I'll have it like this. So the right-hand side is A squared. And this is equal to 1. So therefore my A just square root N. So this means that A hat N equals square root N like this. And homework will ask you to derive A dagger applied to N, something like this. So that's the entire expression. I leave the remaining steps for the next Monday. So I will assign homework today, and then make sure you turn in homework today. And when I grade them, I will leave that in your mailbox. Make sure, go ahead. I will leave that in your mailbox. Here's some of everybody. I will leave that in your mailbox, and make sure you do turn in. Next Wednesday will be a quiz again. That quiz, I decide will add extra points. These extra points will go to the exams. Because not everybody did a good job on exams, so I just want to give you a boost. So, and some points I will highlight them. This go to exams. and this will go to the quizzes. So make sure you do it really, really well. That portion will cover the material mainly in this particular chapter, but the exam portion, some of the exam portion will be from last 2 chapters. And I will write it explicitly. This is the makeup, maybe bonus exam for the last exam. Even if you did a very good job, but you still do it because this will compensate your second exams will be very nice. Because we'll weight the exam versus the quiz is different. So just to make sure you do that. All right, sounds good? For this reason, I will give you extra maybe 5 minutes. You get 35 minutes to finish the quiz. Maybe more. I can't do it. Sounds good? Any other questions? Okay. All right, sounds good. All right, so we're going to end this now. Make sure you do finish the homework on time and turn them in.